Okay, there was that one problem. It's useful. So what do we have? This f of x. This is from homework number 1. I think this is the main one, because the other ones will be dealt with on homework number 2. But what did we have? We had f of x equals 1 plus ax over 1 plus bx to the 1/2 power. And we wanted a linear approximation to that, and we get f of x equals, what do we have? 1/2 a minus b. Oh, 1 plus, sorry. 1 plus 1/2 a minus b. That was the second part of it. So yeah, 1 plus 1/2 a minus b. Okay, so that's a nice clean result, and you can just see what's going on here. And what some people do sometimes is they're taking this pretty major derivative here, and they kind of leave the derivative there instead of simplifying it to this here. So that's a big problem in that you're not getting clarity, right? What this approximation is supposed to do is make things really clear. For example, and this thing contains a bunch of important results. Suppose b is equal to 0. If b is equal to 0, and in fact, how about if b is equal to 0 and a is equal to 1? Then you actually have 1 plus 1/2 x, and that's the kind of the well-known approximation for, root 1 plus x, that kind of thing. So we're trying to get something, and you gotta admit, this isn't that clear. Its derivative is a mess, but this is very clear. A equals b, that's kind of a nice one. That's 1 over 1. So anyway, when we do our Taylor expansions, our goal is to get something that is very clear in terms of what it means. Okay? And of course, this is always a straight line of some slope. We can have all kinds of slopes there, which is a straight line. When x equals 0, it's 1. So it's a straight line of some slope through here. So that's that approximation. Now let's go to a couple other ones from the subsequent homework. So I'm going to do the first one on homework number 2. Okay. And so homework number 2, problem 1. Problem 1. We wanted an expansion f of x minus 1 over x. And we wanted to expand about x sub 0. I'm going to go ahead and sketch the graph, and I'm going to do a large one so that we can put some detail in here. We know that this function looks for positive x, looks something like this. Okay. And we're going to expand it around x sub 0. So what I did was I asked for first order and all orders. Okay. And you could just do all orders and peel out the first order. But let's just go ahead and look at the first order. Expansion and approximation. Then we're looking at f of x equals f of x 0, f prime of x 0, x minus x 0. Okay, and since we have minus 1 over x, we have f prime of x equals 1 over x squared. F prime of x 0 equals 1 over x 0 squared. And when we put all of that together, we now have f of x equals negative 1 over x. And I can could either write an approximation sign, or I'll just add a couple of things. And we'll have the first one minus 1 over x 0 squared. I'm sorry, minus 1 over x 0 plus 1 over x 0 squared, x minus x 0. So yeah, this is a point slope formula. Move the color. So we're over here at x 0. So this would be minus 1 over x 0. And then the 1 over x 0 squared is the slope. And plus and so on. But if we just leave it at this formula here, which is this one, we're looking at the equation of the line that's tangent. So the next ones are going to be in higher powers of this x minus x 0. Sometimes people, this one was simple enough not to make that mistake, but the prior example shows sometimes people will just leave this complicated expression for the derivative in and not simplify the derivative enough so that you just have that expression there. The simple expression. Because remember, these are constants. These are constants. So we'll just continue on with this example. So there's the equation of the straight line. And we had second derivative was minus 2 x to the minus 3. Third derivative was minus 2 minus 3 x to the minus 4. And at this point, it's looking pretty good. How would we generalize to the kth derivative? We would have minus 1, since that was the third derivative, we could do k plus 1 or k minus 1, we do k plus 1. And then we would have, we see 3 times 2, so it would be 4 times 2 times 2. So we have the k factorial, and then we have x to the minus k plus 1. So what we're going to do next is put this into the general Taylor expansion expression. So this was the one goal. This was to get the first order. And for all orders, I'll go ahead and erase here. So all orders, we have, first of all, the definition x, 1 over kth derivative x naught k factorial x minus x naught k equals 0 to infinity. So what if we plug this into here now? Let's see what we get. Take the sum. We'll take minus 1 k plus 1 k factorial. Here I'm going to have a k factorial. I'll go ahead and put this negative power down here. X naught to the k plus 1. X minus x naught to the k. Now, then we get a cancellation, and you could think we're done, but we haven't achieved clarity on this thing yet. So formally, we should have everything here. Go ahead and erase this. And we'll actually do steps. So if we do that simplification, we have the minus 1 This one, we really recognize what's going on in my red curve. And this one, we have to extract out what came, what we had there, and then keep going. Actually, I'm gonna erase this one. Yeah, so in order to really see what's going on here and make sure we get it right, let's just take a few terms. So k equals 0, minus 1 to the 1, x naught to the 1. So that's our minus 1 over x naught. And k equals 1 minus 1 squared, we get a plus x, and let's back it up. 1 over x naught squared, x minus x naught. So that's what we just had. And then what do we get for the next ones? Minus, it's going to be alternating. 1 over x naught cubed, x minus x naught squared. Do one more plus 1 over x naught to the 4th, x naught cubed, and so on. So when you write it out this way, the whole idea is that this is a small quantity. Another reason to have the closed form is you can actually do operations on the closed form. You know, if you were to say take a derivative of this, you got all infinite derivative stuff. But these two here were the ones I just graphed, and then you can see what's going on. You're subtracting off an x minus x naught squared, so you're coming in closer here, right? You're just getting better and better approximations as you add those terms. Okay. And why is this so important, this function here? You have the Newton potential, right? It's very important. Coulomb potential, Newton potential. So just knowing its formal properties and that type of thing. So the takeaway from this is that, you know, we do the formal version, but we have to make sure we really see what's going on with it as well. And the other thing that I mentioned in the context of that first problem is that these derivatives have to actually be evaluated and simplified as much as possible. Okay. So, good. So that was the first one on homework number 2, and the other ones were similar. Minus 1 over x squared, the natural log. So all those things, good. And then, and then going through those problems, hyperbolic cosine and sine, we wanted to make sure that the derivatives are simple because they were just 1s and 0s. Right? 1s and 0s, anything else? That's pretty good. Okay. So the next thing I wanted to talk about is put a list of what the current assignment is. Since and if you guys have any questions about any of these, we can discuss these now as well. And then to get a list of the current assignment up here, maybe work on that together as well. So that we're all up to speed this week. So I'll raise this. But yeah, this is a major topic, and you know that when that exam comes up in a couple weeks, we'll definitely have a couple Taylor expansions on it, right? Some interesting ones, hopefully. So that's a major topic. Good, so maybe we can assemble the current list. You guys can tell me what's on the list of current problems. Okay, okay, so yeah, well, help me out. What are they? The one we did. Oh, nice. Okay. I'll just write else and sum over k minus 1. Okay, yeah, we did that one. That's good.
There's also the other one we did in recitations with magnitude of C1 plus C2 being less than or equal magnitude of C1 plus C2, the triangle and equality.
Triangle and Yeah, so that one got mixed between sets. So z to the n, if you didn't do it yet, yeah, definitely that's a good one. It really thematically, it goes along with, like if you do this one first, it helps you on this one right here. Okay, good. So then what?
They're showing that the real Fourier series or whatever follows from stuff.
Okay, follows from the complex, good. We may look at that one some more. The real Fourier series. Then we must have had two actual series, right?
Well, there's the f of x equals magnitude of x and f of x equals x.
Okay, great. And that was as far as we had taken. Good. Good. Yeah, I actually want to go over some of these, maybe one of these together, you guys do the other one type of thing. Actually, I have a couple ideas. Let me get this concept.
I also had, was it showing that pi over 2 is sub pk sine k pi over 2?
Yeah, you know what? I'm going to start off with one of those. So when we get these Fourier series, we can also get some interesting sums, infinite series summations. And I had to look at, in fact, you know what we'll do is here, so we'll start with the Fourier series that we had already done. And just take it from there. So I'll collect these formulas here on the left side of the board. So we had done this complex one, and I want us to do at least another one of these before we do the real ones, or while we're also doing the real ones. So we've got that Fourier series with the complex exponentials, and the c sub k is 1 over 2 pi minus pi to pi. And we have to get some practice with these. Minus ikx dx. So we had that in the example that we did, was the step function, which is a great example. So the example was f of x was negative 1 minus pi less or equal to x, or we'll do strict equality less than 0, plus 1, 0 less than x less than pi. Okay. So we did that, and we will sketch it here underneath this thing. On n minus pi. So the result we had for this was f of x equals sum over, just to make sure I get that right, we have 4 over pi sine of 2n plus 1 x over 2n plus 1, if you're summing from n equals 0 to infinity. If you sum from n equals 1 to infinity, you'd have 2n minus 1, 2n plus 1. So, one or the other. Okay. And we didn't see, you know, if you add up a few of these, you're starting to get something that, you know, goes like that. And 4 over pi is slightly more than, you know, 1/4. So we get this overshoot stuff. Okay. Now what's interesting here is that if you take, say, pi over 2, f of pi over 2 is just equal to pi over 2. of pi over 2 equals pi over 2. And there's how we're going to get this infinite series. So we've got 4 over pi 2n plus 1. And then we have sine of 2n plus 1 times pi over 2. So these are all now just numbers. Okay? So when n is equal to 0, we have sine of pi over 2, which is 1. Okay? When n equals 1, we have sine of 3 pi over 2, which is minus 1. N equals 2, we have 5 halves pi over 2 plus 1. So we get this alternating series of plus and minus 1s right here. So we can plug that in, and we're going to get pi over 2 is equal to 4 divided by pi. No, not pi over 2. I'm thinking of the wrong one. This is 1. Okay. We're just on this constant there. So 1 is equal to 4 over pi times these alternating terms. So, oh, and then this is pi over 2. And it's 2n plus 1. Here we go. So we end up with 1 minus 1/3 plus 1/5. So there's an alternating infinite series. Minus 1/7 plus 1, etc. So we can just multiply both sides by pi over 4. And we're just left with what's here. So 1 minus 1/3 plus 1/5 minus 1/7. And I thought we should do a few of these as we generate these Fourier series. This one does not converge very fast, but if you want to plug it into the calculator and generate some of these, you got to get quite a bit. What's pi over 4? It's like 0.8, less than 0.8, 0.7, 0.75, 0.7, something like that. So anyway, this is how we can generate some infinite sums here, and we're confident that that these converge here. Good, so that was what was meant by that assignment, and I was just asking for it on a couple of the other ones as well. But yeah, we were able to do this on this one already. So let's look at one of these two and maybe do it together, and then that'll help you through the other one, the real Fourier series. Okay, so the next step would be to look at the real Fourier series. Here we have the complex one, and we have to have them both complex, real, and then we have to have the arbitrary intervals, all that stuff that we've already taken a look at. Good. So, but yeah, does that clear that up, what that problem was there? Getting those infinite series? You can get a bunch of them. Every time you do a Fourier series, or often you can generate a different version, and you can look these up in a handbook of math sometimes. You'll have whole pages of these. I think during the Great Depression, they were hiring people to crank these things out. That's my story anyway. Okay, good. So let's leave this, I'll erase everything else. And what's noteworthy is we used this form, and then as we evaluated it, we just got the real. It was a real function to begin with, we get the real Fourier series. So the real version of the Fourier series is also very useful, and it takes the form like this. We take a0 over 2 plus sum over k equals 1 to infinity, a sub k cos kx plus sum k equals 1 to found last time, I kind of led you through it, so you're just gonna have to take that note, those notes and run with them. What we found was your a sub k is now 1 over pi f of x cos kx dx, and the b sub k is 1 over pi sine kx dx. So this was the one we proved. And we used that interesting relation with exponentials to prove it in just a couple lines. So the idea is to take this and then generate this by showing that you get all these terms. And the way I had done this, I can do it for the b sub k. Maybe I did the a sub k last time. I'm just gonna make contact with the c's. So I've got minus pi, but my f of x, but my sine of kx, I can write as 1 over 2 I e to the I kx minus e to the minus I kx. And so b sub k, I'm just going to factor out the I here for the moment. I've got 1 over 2 pi integral minus pi of pi f of x e to the I kx. I'm going to do this. Minus f of x e to the minus I kx. And the point is, as you expand this out, you're making contact with these. Right? So you're going to see that relation between your A's, B's, and your C's, and you can, you can say, express b sub k in terms of c sub k, c sub minus k. And actually, so having demonstrated that, you could say the homework would be to express a sub k and b sub k in terms of, the set of c sub k. And it's always c sub k, c sub k complex conjugate. Right? They track k will, the index k will go with the index k here, vice versa. So that's a good exercise in terms of getting to recognize these things, right? There was your sign, and you just get used to using this form, and when you do, suddenly you're over there, okay? So that one's well worth your time. And we have most of the way there, we're kind of looking at it already. Good. So then we could say, look at this one. And then this one will, be a slightly more involved version. So I'm going to leave the left side of the board up and just erase all this and look at this one here. So what we have with these real ones is that depending on whether, if a function is purely, if a function is even, you get rid of some of these. If it's odd, you get rid of some of the other ones. So that's what we're going to talk about next. It'll save you a lot of trouble there. So next we'll consider f of x equals x. That's an odd function. This was the even one that we had been talking about. x an odd function. And there it is. It's like that, pi minus pi. So base of k equals 0 for all k. Cosine is even, f is odd, product is odd, and the integral therefore vanishes for all the a's and k's. So the b sub k's, which is all we need to have, are 1 over pi minus pi to pi x sine kx dx. So for this, and you know, if we had x squared or x cubed, it would just get worse, but for this we have to do integration by parts. So the integration by parts will have x times minus cos kx over k minus pi pi minus integral minus pi to pi. This one would take the derivative of negative cos kx over k dx. So what do we have here? The integral of this is going to be a sine of kx, right, over k squared. And the sine of kx pi to minus pi is going to vanish. Right? K pi, sine of k pi vanishes, sine of k times negative pi vanishes. So without having, we don't have to actually do this integral because we know it vanishes. And then this one here, we'll have 1 over pi negative cos k pi over k minus negative pi negative cos k pi over k. And we see we get 3 minus signs here, 1 there, so pi's cancel. And we'll get minus 2 cos k pi over k. And what about this cosine of k times pi? Starting with 1. So cosine of pi is negative 1, cosine of 2 pi is positive 1, and so forth. So this itself we can take as a minus 2 over k minus 1, k equals 1 to the k equals 2 over k negative 1 to the k plus 1. See if that's what I said yesterday. Indeed. Fantastic. Okay, so we've done that work. We have this thing, and you kind of see as you're working through, you're checking to see whether I have to do an integral at all, right? And we got them all to 0, and it's so easy to get lost in the minus ones. That's just part of life of this subject. You usually do it a few times. So now we can go ahead and plug back in and see what we have. So our function f of x equals x. So between minus pi and pi, we have sum over 2 over k minus 1 to the k plus 1 power So that was the b sub k, and then we have the sine of k times x. K equals 1 to infinity. And then in keeping with what I had just said a little while ago, we want to write a few of these out, okay, so that we actually kind of recognize what's going on. And so I'll put this here. So for the homework, write out first several terms. And the other thing we could do is, why not, evaluate at x equals pi over 2. Because that'll give you good practice in generating these things here, right? And then this time, if you evaluate at x equals pi over 2, you know, you're gonna have sine of k times pi over 2. So the first one's going to be 1, second one's gonna be 0, third one's gonna be 1, fourth one's gonna be 0. So you're getting rid of a bunch of those, okay? And what do we end up with? We actually get the same one we had on the other one. Yeah, we actually get the same series for, which is very nice. Okay, good. When you evaluate x equals pi over 2, you get the same infinite sum equaling pi over 4 if you want. Divide by 2 that you get for the other one, which is a nice consistency check. If you were to do, and I'm gonna have to assign one of those, if you were to do f of x equals, say, x squared, and you do that type of evaluation, you're going to get expressions for pi squared over something. And again, you can find those in some handbook of infinite series, and you'll know where they came from by doing that as well. So maybe I'll add one more of those. But yeah, this is how we want to take these through. So this problem, you just add, write out several terms, evaluate x equals pi over 2, and see what you get. So that and that last problem take us through this week's assignment. I guess anything I assign now will be on the next one. Okay, that's good. That's pretty gratifying. So now, good. I'm gonna assign one more real Fourier series, and then we'll have a little collection of these, okay? And good. So I'll keep leaving this up here. That'll be the other major topic on the exam. Taylor series is a complex number. We'll have to knock out a Fourier series of some type. So I'll add this homework problem for next week. We want to expand in a Fourier series f of x equals pi squared minus x squared. Why did I choose that? Nice and symmetric and has some good numbers. So let's look at the graph first of all. So I've got pi and negative pi. And if I'm up here at pi squared, you can see I've just got this parabolic segment there. And this is an even function. So it's just going to have the a sub k's. And because it's got an x squared, you're not going to love it, because because you have to integrate by parts twice. But it's good, you know, the a sub 0 really just sets an average value of this thing. That's what the meaning of that, integral is. So this Fourier series would be very closely related to the Fourier series for x squared. Okay. Suppose you had f of x equals x squared. And, you know, pi to minus pi, and right, that looks like that. So the difference between these two Fourier series is going to be, this one's going to have that 0 term, and it'll be flipped upside down. So if you know this one, you can actually just infer this one without much trouble. They're that closer to it. And then, having found this one, real Fourier series. And then the second thing, this is becoming a habit, right? We'll get an expression for pi squared, right? Pi squared equals f of 0. But that one's not going to be so bad because look, it's going to be the cosine series. These are all going to be ones. You don't have to monkey around with any alternating things, right? These will all just be ones, and so it'll be the sum of those will equal pi squared. And what you'll end up with is pi squared equals this equals that constant term plus that infinite sum, and so yeah, you'll see when you get there. Okay, you want the real Fourier series, etc. So you're going to find the infinite series. For pi squared, but I'll just see if I can put it back up there. Yeah. Actually, I end up with a pi squared over 3. But yeah, once you have one, you have the other. I think the simplest form is you end up with a pi squared over 3 equals or we could even do pi squared divided by 12. I think pi squared divided by 12 will be the simplest one because it'll start with a 1 and then it'll be minus something. So, right? Pi squared is about 10, so 10 12 is 1 minus something. Okay. But anyway, yeah. Good, that'll be good. So now I want to look at something that we can't visualize as much. And we'll use the complex series again. Okay. So can I erase this? Was this the first one for next week?
Yeah.
First one, good. So we'll look at one more problem using the complex, and then we'll go into those arbitrary intervals and stuff that we had last time. So example, I think this will also be a homework problem. So suppose you're trying to create a signal that consists of a bunch of pulses. Pulses, say, in time, but we'll do it in x for the moment. Then we could change that to time later on. So I'm going to do this, minus pi to pi, 2 pi, 3 pi, but my pulses are like this. From pi over 2 to pi, I have a pulse, you know, some height c. So where does the next pulse show up on this graph? 3 pi, 4 pi, 5 pi. Because we know these are periodic functions. So what I'm looking at pulse, and then I go out to here, I get another pulse. Okay. That would definitely be the generation of some kind of signal, right? A set of pulses, because they are gonna appear in a certain rhythm. So, to find that, it's neither even nor odd. Okay. So we would have a whole bunch of integrals to do. And if you did all the real ones, I'm not saying the complex one's much easier, but you're just not gonna see anything. That result is gonna be true, and that series expansion is gonna be true, you're not really gonna see much, okay? Especially in terms of the form of these coefficients. So what if we do the complex Fourier series for this? Since we're not gonna see anything anyway. But we may, we could use that to generate whatever the signal we want here. C is a bad letter to use. I don't have a letter on the thing there. We could even just do 1 for the moment, arbitrary constant. Okay. So what do we do here? We say, good, it's this. C sub k equal ikx. Infinity to the plus infinity. 1 over 2 pi. So what's the integral here? Easier than you'd expect. How do I calculate this integral? This one. For that function I just drew a picture of. A machine can do it. Anybody? It's just a function that's equal to 1. It's e to the minus ikx. It's just all about the boundaries, so I just go from pi over 2 to pi. So that's not difficult at all. So you can generate this thing and write it down, and you'll have all the terms in a machine that then go ahead and calculate it for you. But you're not going to get any more wise by staring at it. Okay. But you know what? I'll put this as a homework. It's just going to be 1 over I, this and that. It's not going to be a big deal. Equals homework. Up with that. You've got e to the minus I, k, pi over 2, pi, and so forth, and things like that, okay? So those could be expressed in terms of I minus 1 with something. If you can find a simple way to look at that. But yeah, then you're already generating a signal. If this were a time axis, then you're generating these pulses. And how are you generating them? By adding up a bunch of standard oscillating functions. You're going to need a bunch of them, but that's what's going to happen. Okay, good. I think this gives us some practice in this subject. Once you get down there, roll up your sleeves and do them all. We'll also be talking about these things in general terms, and then we've gotten some practice with them. Okay, so when it comes to the general terms, we can kind of just really, we're just going to repeat what we had last time and add the time axis as well. Yes, we have that. Okay, good. So I'm going to go ahead and erase this. This is that problem. This entire set of formulas are all related. the interval minus L to L. We need this one. We had it last time. So in the case of the C sub k, we had e to the I k, and then what did we do to modify this arbitrary interval? Just to retain the 2 pi periodicity, we just had pi over L x, and then when x is equal to plus or minus L, we had e to the I k pi. So this is no problem. And we had C sub k over 2L minus L f of x minus I k pi over L x. So good. Minus L to L. What if we're using time now on this axis here? Then we might be interested in a periodic event that goes from minus t over 2 to plus t over 2. So suppose we had f of t, we could have c sub k e to the I k. K is just the interval. So what do we have here if we have time? We could have pi, instead of L, we could have a t over 2. Right? The idea here is that since we're doing a periodic thing, we want this to be t over 2 on the t-axis. And so then we end up with I k 2 pi over t. And then c sub k is 1 over t in this case, because we're going from t over 2 to minus t over 2. Okay. F of t, so t over 2, t over 2, e to the minus I k 2 pi over t. So we want to be confident that we can do these. The ones we do for homework are always just going to be these. Okay? We don't need to add that. However, one thing to recognize, what is this? What's another word for 2 pi over period? That is a frequency, right? That's like an angular frequency. So when we turn this into the Fourier integrals, we're actually going to have them in terms of k and x, where we'll have, x would be a length, k would be a wave number, and we'll also have them in terms of omega and t. So that'll come when we make those, when we make that transition. And what happens then is, what we're mainly setting these up for is next time to take the limit L goes to infinity. Okay? The limit L goes to infinity is a little tricky. We may as well start talking about it now. Because like I said, any of the concrete problems, we're just going to use these formulas. Okay? We don't have to complicate it with extra factors of time, what have you. But suppose we wanted to let L go to infinity. Well, you can't just set L equal to infinity here. Right? You've got that problem and in here as well. So that limit's a very interesting one, and it takes us to the Fourier transforms, Fourier integrals, which they can be a lot better than the Fourier series, a lot less fiddly. For one thing, it's one integral. Okay? That you can do. But yeah, that's where we're headed. So do we have enough homework for next week? Well, we have those two. That's enough for us to chew on Monday. Good. That's all I've got for you today. So we're going to do next next time, we can review this stuff if we have to, and then we'll go right from here into that limit, L goes to plus minus infinity. Okay, good.